once I understood that my device was marginal instability, I mean it's close, it's unconditionally stable, but I don't think I could hold that over any sort of manufacturing tolerances, I wanted to see, just based on my bias, what would happen. So it's very easy to select a couple of items to tune or to vary while I'm watching the simulations. And here we can see we're just varying those bias voltages. And this particular device, we are getting closer to the FOT of the device than maybe most designs. So the device definitely had a sweet spot from around 4 to 8/10 of a volt on the gate. And I found that when I went much above that, I actually lost stability. My stability went down considerably. It went up slightly in that 0.4 to 0.8 range than 1.015, but not much. It really sort of hung right there, leading me to continue to believe I'm right on the edge, and we really need to focus on stability before we worry about even designing any sort of amplification stage. So based on this, I wanted to add some sort of feedback to try to improve the stability of the device. But before I did that, I wanted to understand what my options were. So I synchronized the layout of this device from the schematic to the layout, and just placed some bulk vias to ground, so I could understand, how am I going to, if I wanted to do some sort of source series feedback, how that would look, or if I wanted to do some other type of feedback, what sizes would I actually end up with. So series resistance in the source is a very classic way of improving our stability. It looked like, here I could easily move my vias out a little bit, have some air bridge coming over, mounting a little bit of resistance, and then down to ground. So that was the first idea to look at, and I went ahead and mocked that up. But I noticed that although it did tune things by adding the additional inductance and adding the actual via models themselves, it also looked very sensitive. It had moved it quite a bit. And so I started just by trading off, or just varying the line width lengths a little bit, and just varying the line lengths, or actually moving that via in and out, pretty dramatically moved my stability factor around. So I could see that anything I was doing in the source was very sensitive area, and if you try to go ahead and in any design make it build it to where you're relying on something that's very sensitive, you're going to have manufacturing problems, and you're going to have designs that are tightly cued, highly tuned, and are easy to move around and very easy to miss your design. So I tried to add a little resistance there just to see if it really did what I was expecting once I saw the initial line length insertion, and it does. As soon as you start to add any sort of resistance to try to give yourself a little additional stability, it knocks it down very quickly. So right again, just going from 1 to 5 ohms, we're back on the edge. So any small variations there, we're looking not very doable. So another very traditional way, or classic way to improve our stability, is to look at the gate to drain feedback. So I thought, let me mock this up. But when I'm looking at it on the schematic, it's very hard to envision how is this going to get mounted, because I've got a device, I've got vias there, I've got other things going on. So fortunately, I could easily synchronize my schematic elements to my layout again, and then once I'm in the layout, with the additions to the newer PDKs that TriQuint has made in conjunction with Agilent, it's very easy to do this routing. So I quickly routed a line around the upper vias. You can see here on the left, just to route my traces. I was able to insert vias automatically and pop up to different levels and wire up my capacitor and my resistor. Once I had that, it's very simple to extract the parasitic transmission lines, or to understand what the transmission line model of this particular feedback would be. So I went ahead and modeled the transmission lines, and gave me an idea of what this was going to look like from the standpoint of a schematic model. So taking this back into the schematic, using these line lengths approximately, I'm not worried about all the bends and everything yet. I'm just really worried about what it's going to take to get me kind of routed around that via and in the right area, because we know we're going to still be moving things around, doing some tuning and things like that. So, but I can just see that with the initial line lengths that we're talking about, I helped my stability. It improved it 40% or so, and it's something that I can already see that I'm going to be able to build here. And because of the sensitivity of the source area, I've included the vias and some transmission line to get to those vias. So I started by looking at something just really basic here. How does this this transmission line feedback and resistance work? I think I skipped a slide, excuse me. Nope. So I did some initial tuning again. We brought up the tuning environment and moved those transmission lines in length, changed their impedances, varied the resistance, and it didn't affect things greatly. It affected it slightly, as you'd expect. So I rigged up a Monte Carlo simulation of that particular area to see what would happen when I'm varying my process. So I'm varying the process as well as the match or the stability structure around it. So I'm letting the microstrip media vary as well as the devices themselves. And I let the transmission lines vary considerably, up to 50% in length. So this really had a pretty good stable spot from about plus or minus 50%, 150 to 50 microns on the line lengths. And it showed me, even though lower down in frequency I'm getting some instability regions, I may have to watch out for some oscillations on the lower side. Certainly in the band of interest that I'm working in, it's very stable, and it seems to be stable over manufacturing tolerances. So looking at this, I was fairly satisfied with the stability I'd locked in. And then I was more interested in next starting to think about the matching. So if I've got a good stable device, my next course was to get a good unconditionally stable match. I want something that there's no possibility, given whatever impedances that I present to this amplifier, that I can go into oscillation or get unstable conditions. Within ADS, there are some routines, they call them smart components. I can actually have it generate for me an initial matching condition. That is certainly one way to do it, and often quick matches, it's very convenient for that. I get some new device, I just want to see what it might look like, not really intending to get a true physical match with it. So I'll often just quickly use those. But another method is just conjugate matching techniques, which is traditionally how I've done this. And if you haven't done this before, there's an exceptionally good reference and many, many books on this topic. But this particular reference for the app note 95.1, it's a very long traditional app note that's been in industry for many years. It was created when Agilent was part of Hewlett-Packard, and it's available at this website, and it'll go through how to conjugate matching techniques. So looking at just basic roulette stability analysis with conjugate matching techniques, and thinking back that I am trying to minimize the lengths of any stubs I have coming off my main line, I opted for impedance matching on the output. It was an area where I could see that I could, instead of putting a stub, I could do an impedance match. So even though it's a lower impedance transmission line, I opted for that method. And once I looked at this, I was able to, with a little bit of tuning, waiting for the trace to come up here, you can see with a little bit of tuning, I was able to center my gain as well as my match and get pretty much what I was expecting out of the device. So without really super tuning the device, there's always some danger that if you get your matching too tuned, very, very narrow banded. As you cascade the stages, that effect just gets worse and worse. You get such a high Q device that you really can't control where you're getting your gain out of it. So reasonable amount of gain coming out of it, nicely matched, and a fair amount of bandwidth considering the bandwidth for this particular application, again, was very narrow. So then I started cascading these elements together, and my output stage and the stage before it were getting me pretty much the output power and the gain I wanted. With the lower power from the baseband coming in on the left, I wanted just a little bit more gain out of that device, so I shortened it up. So instead of a 50 micron gate length, it was 25, which on its own pushed stability up. So I chose not to put the feedback on that particular device there. But at this point we stopped, and I tried a couple of different configurations to see if I could get better gain out of that first and second device. And I tried a cascode pair, and it was close, but I was actually still getting slightly better gain out of the cascaded approach here than using a cascode. And what I've done here is interstage, I've brought every stage to 50 ohms. So I'm matching just classically 50 ohms and putting the stages together. Given where these impedances were, when I tried to match directly from the input of one device to the output of from the output of one device and the input of the next, the structure got longer. And as that did, the losses were actually knocking my gain back down, so I was not really getting any benefit from doing interstage matching between the two. Now, if that had been giving me some benefit and I wasn't coming out to a clean 50 ohm point or a 50 ohm reference somewhere or some sort of impedance reference, there's a technique in ADS using something called test labs, and basically what I could have done was to cascade all three of these devices together within the test labs, and I could have looked at interstage matching while I was doing this. It was something I didn't get a chance to get done on this, but sometimes when you're having those interstage problems, and maybe you're doing 3, 4, 5, 6 stage amps, you're able to look between the devices. You're able to look at the overall performance while you're looking at the interactions between individual stages via test labs. So there's an example within the ADS example structure, and if you have some issues with it, please contact your local Agilent support team, and we can help you out with that. So kind of tuning this one up, it just took a little slight tuning. I was able to get close to 27 dB of gain out of this theoretically here, and I could have worked a little bit more on my output match, but again, we had to get this built, and so far all I had done is get the design with empirical transmission line models, and again, this was kind of a short time frame that we were working with here. So looking at it, looked fairly centered from where I wanted to work from a frequency standpoint. I was getting the gain out that I wanted. I was a little concerned about what this would be doing from a nonlinear standpoint, so I did run some compression on the device to look at what the linear range was. And then ADS also has